Hi, this is Mrs. LaBarbera. This is AP Physics Chapter 2, Video 8. Today's topic is Velocity and Position by Integration Part 1. The objectives for today is to be able to determine change in velocity and displacement using integral when acceleration is not constant. Finding Vt and xt when given at. In the case of straight line motion, if the position x is a known function of time, we can find Vt by doing the derivative, Vt equals to dx over dt. And we can use Vt to find at by doing derivative, at equals to dv over dt. We can also go backwards. If we're given acceleration function, axt, we can find velocity function, vx. And from vx, we can find position function, xt. How do we do that? We do the area under the curve. So let's review the area under the curve when acceleration is constant. So in AT graph, the area under the curve represents velocity change. That's Vt, v at t2 minus v at t1 equals to the area. In Vt graph, the area under the curve represents displacement, which is the position x at t2 minus position x at t1. So if we know the acceleration and the time interval when acceleration is constant, we can figure out this area easily. We know the formula for rectangle and the formula for the area of a trapezoid. If acceleration is not constant, how do we find this area though? When acceleration is not constant, the area have the same meaning, but how do we determine this area? Let's zoom into the area. To determine the area under a curve, we break down this area into tiny, tiny rectangles. Now each rectangle represents change of velocity. How do we know? Because the rectangle, the area is delta t times a. What's delta t times a? Delta t times a is change of velocity during that time interval. How do we know? Because acceleration is defined as delta v over delta t, so delta v equals to a times delta t. So the total area, so each area is a tiny change of velocity during a time, very tiny interval, delta t. The total area is total change, is v at t2 minus v at t1 equals to sum of total area. So at times delta t, this is the area of the strip. This symbol, sigma, is the sum of all the strips from t2, t equals to t1 to t equals to t2. Now in Vt graph, the total area under the curve is the displacement. So the total area is the sum of tiny area of strips. So each tiny area is Vt times delta t. This is the tiny displacement during the time interval delta t. And you add all the delta x together, you get a total displacement. When delta t approaches to 0, a different sign is used. Instead of using sigma, we use integrate sign. This is like s, sum, represent sum. So this sign, like stretched s, is called integral. So now when t approaches to 0, the velocity change equals to the integrate of at times dt. What is at times dt? At times dt is the area of the rectangle. So basically, it's the same idea. You add area of the rectangle all together from t1 to t2, you get a total velocity change. Similarly, for displacement, you add the area of delta x. Vt times dt is your delta x, then you get a total displacement. So if we set t1 equals to 0 seconds, when we can determine Vt and xt at any time. So t2 becomes t, t1 becomes 0. So Vt equals to the integrate from time t equals to 0 to any time t of at dt plus the initial velocity at 0. Similarly, any position at any time t is integrate of vt dt plus the initial position x at 0. Finding antiderivative. So with these two equations, if we know at, we can find vt by doing the integral function. Similarly, if we know vt, we can find xt by doing the integral function. But how we are going to do that? When we're dealing with situations where we have to integrate, realize what we're given, at. What is at? At is the derivative. We're given the derivative. We're trying to find original function, v. So this is the case of working backwards to find antiderivative. So to find that, let's use an example. An object starting at origin at a time t equals 0 is moving at velocity with respect to time according to equation vt equals 2t. What is the position function? So this is to find original function. What was the original function before the derivative was taken? So what function whose derivative is 2t? Think about it, that's t squared. So let's use this equation xt equals integrate of vt dt plus x at 0. We know it's starting at origin, so x at 0 is 0. We substitute vt equals 2t. What is the original function whose derivative is 2t? That's t squared. T squared plus 0 is just t squared. So the position function is just t squared. Next question is how far did it travel from t equals 2 seconds to t equals 7 seconds? This is a displacement. So this is asking you what is x at 7 minus x at 2. So that's 7 squared minus 2 squared to give you 45 meters. Let's take a look at another example. The equation for a particle's acceleration is given by at equals 6t minus 3. The particle starts at rest from the origin. So that means v at 0 equals 0, x at 0 is also 0. What is the velocity function? So velocity function is the original function whose derivative is 6t minus 3. So what is the original function whose derivative is 6t minus 3? That is 3t squared minus 3t, right? Going backwards, 3 times 2 times t, which is 6t. 3t, the derivative of 3t is 3. The original function, let's take a look at this. So vt is the integrate of at dt plus v at 0. V at 0 is 0. So we just have to find original function for at, which is 3t squared minus 3t. That is your velocity. So next question is, what is the position function? To find the position function, we have to find original function whose derivative is 3t squared minus 3t. What is that? That is t cubed. And the second 3t is 3 divided by 2 times t squared. Because 3 divided by 2 times t squared, if you do derivative, that's 3 divided by 2 times 2t. And 2 and 2 cancels, give you 3t. So that's the original function. So xt equals vt dt plus x at 0. X at 0 is 0. We know that already. So original function for vt is t cubed minus 3 over tt squared. That is a position function. So in summary, so basically derivatives are used to find the slope and integrals are used to find area. So v is the slope of xt graph. So v is dx over dt, because derivative is the slope. Similarly, a is the slope of vt graph, so a is dv over dt. Now, delta v is the area of at curve. So delta v is the integral of a dt. Now delta x is the area under vt curve, so delta x is integrate of v dt. That's it for today. Thanks for watching. See you next time.